Hello, we are going to start with a couple of elementary notions. To start the course, we need to see the difference between linear equations and nonlinear equations. So basically we are going to focus on linear equations, but it's good to know the exact difference. And variables of the system, we are going to call our unknowns variables. That will be useful. And also something that is specific for linear systems. Regarding their solutions, either we have a linear system with no solution at all, or linear system can have exactly one solution, and the last option is the linear system has infinitely many solutions. This means that our linear system cannot have, let's say, 2 solutions or 3 or 7. There are only 3 options. We have a linear system, either that system has no solution at all, which means there's at least one equation that is in contradiction with others, or the system has exactly one solution, or the system has infinitely many solutions. And when we have infinitely many solutions, we will have free variables and parameters, so this will be written in a special way. We will see some examples for that. So first thing is linear versus nonlinear. So that's going to be presented with a couple of examples, simple ones. And then we are going to go for a couple of linear systems just to illustrate these 3 possibilities. And later on, we'll make it more complicated. So you know, if you have x squared equal to 4, well, that's a nonlinear equation. And that one has 2 solutions, 2 and minus 2. That's nice, there's no problem there. But if I have a linear equation, that's not going to happen. Only one of these 3 options are possible. So let's say I have some examples of non-linear equations. So let's say x squared equal 4, or radical x minus 2 equal 1, whatever. X1 times x2 plus 3 log x3, let's say equal 1. So all these are nonlinear. You have a variable to a power, that's nonlinear. You have square root of a variable, that's nonlinear. Product of 2 variables, it's nonlinear. Log is nonlinear function. Tan, cotan, sine, cosine. If I have x1 over x2 plus, let's say, sine x2 equals 6. Well, you have ratio of 2 variables. This is nonlinear. Sine is also nonlinear. So these are nonlinear equations, and we are not dealing with them. Our course is linear algebra, so we are going to deal with some linear equations. Some examples. Let's say 3x1 minus 2x2 equal 4. So this is a linear equation. Intuitively, what linear equation is a number times a variable plus a number times a variable equal to a number. I can have another one. Let's say I have something like this. And then I have, let's say, 2x1 plus 2x3 equal 2. So I have these 2 equations, both of them are linear, but now they form a system. How do I know? Well, I wrote it that way. You see, I will deal with both equations at the same time. So this will be something important, because when we are looking for solutions, well, solutions need to satisfy each equation at the same time. So all of them must be satisfied by the solution. We will see some examples for that too. So basically, what happened here, you have x1, x2, and then in front of x3 was 0. So 0x3 minus 3x4. And if you look at this system has 5 unknowns. So x1, x2, x3, x4, x5. Even though some unknowns appear in one equation but not in the other. That's perfectly fine. This equation here had two unknowns, two variables, x1, x2. So we are going to keep this notation x1, x2, x3 because it's general. Sometimes in your book they use x, y, z. It's fine, but keep the general notation as much as you can. Now what we learn here is that you can have a system where some variables appear in certain equations but not in others, which is perfectly fine. And also you can have systems that have here two equations but five unknowns, five variables. That's perfectly fine too. So there are some of the variances that we will see in the class. Also, you see that you have on left side all the variables equal to a number on the other side. When the number is not a zero, the equation is called non-homogeneous. Here also this equation is non-homogeneous. This one is also non-homogeneous. So I'll just write non-homogeneous. This is just introduction of vocabulary. So question is, what is homogeneous? Here is one. So let's say I have this equation. So this one is homogeneous because on the right hand side I have equal to 0, right? And I'm going to add another one. So this system is homogeneous because on the right hand side I have 0 for all the equations. So this will be homogeneous system. This one here is non-homogeneous system because I have more than one equation. That's why it's system. By the way, if I have, let's say, this is homogeneous equation, and then I have this one that is non-homogeneous. Now system is not homogeneous because, okay, one equation is homogeneous, fine, but the second one is not. So as soon as one of the equation is not equal to 0, well, the system is not homogeneous. So we just call it non-homogeneous. For now, it doesn't make much difference, but when we start looking for properties for these systems, this will be something important. Okay? This is just vocabulary for now. So what we like is to keep on this side of the board, we are going to consider only linear equations in our course. All the non-linearities are not considered at all. Okay? So we know now that x1, x2, x3, those are variables, our unknowns, and we are looking for them. Okay? The entire course is about finding solutions for linear systems. What is a solution? Well, it's a list of values for x1, x2, x3, such that when we plug them into all the equations, they satisfy all of them. So that's the idea of the solution. So let's say I have a system like this one. I will not solve it, I'll just check something. So I have x1, 5x1 plus x2 equal 3. And then 2x1 minus x2 equal 4. So this is non-homogeneous system. We don't need to write it every single time. What we want is to find the solution. What is a solution? Well, solution is all about values of x1 and x2. So I'll just write here x1 and x2 variables or unknowns. So this is just vocabulary. And we are looking for these guys, huh? That's what we are doing. We are looking for x1 and x2. That will satisfy this equation. Okay? So the solution will be not one number, but two numbers, ordered numbers, values for x1 and x2. the vectors will be right like this, standing up. And solution is, in this case, 1 and minus 2. How do I know? Well, I need to verify it, and part of your section 1 is about finding actually if a proposed point is a solution or not of your system. So this is linear system. Somebody pretends that this is a solution. How can I know? Well, I need to plug it into each equation and see if this when I plug this vector in, if it satisfies both equations at the same time. So if I replace x1 by 1 and x2 by minus 2 in equation 1, so that's what we need to do. So equation 1 is 5x1 plus x2 equal 3. So I do 5 times 1 plus x2 is minus 2. This is equal to 5 minus 2. This is equal to 3. It satisfies the first equation. Okay, so the left hand side, when I plug it in, is equal actually to the right hand side. Yay, we are happy. So this satisfies first equation. Now replace x1 do the same for the second, because we don't know if this is solution for the entire system. We know that it solves the first equation. So I'm doing this in details, baby steps, just to make sure you understand everything. Obviously, when you need to do it, well, you will pretty much try to plug it in and see if the left-hand side is equal to the right-hand side, and that's it. Okay? So we replace this in equation 2, and equation 2 was 2x1 minus x2 equal 4. So what we need to do is to see minus, so x2 is minus 2, so this is 2 plus 2, this is 4, that's equal to the right hand side, remember? So this couple, 1 minus 2, satisfies both equations. So we see that, so this is the solution, the vector. It's not just numbers, it's both of them in a certain order. So we see that the vector x1, x2, which is equal to 1 minus 2, satisfies both equations at the same time. At the same time is important. Okay. Hence, the couple here is a solution of the original system. When I say original, I mean the one from the beginning. So maybe I could copy it if I have space. Just for you, it's nothing special. It's not original in the sense that it's special, it's just the system from the beginning. Okay? So that's how we verify that this is a solution. So the entire vector is a solution, because our solution needs to satisfy both equations at the same time. And here we have two unknowns, so our vector has two components, and these are the proposals for the solution. Just for fun, let's say somebody proposed another vector as a solution. Let's see if that's true. So verify if x1, x2 equal, let's say, 1, 1 is a solution of the system. from the beginning, this one. So what do we do? Well, we plug x1 equal 1 and x2 equal 1 into the equations. If somebody gives 7 and 11, well, you put 7 and 11 instead. So if I plug it in the equation 1, I have 5 times 1 plus 1. This is equal 5 plus 1, which is 6. Well, this is different from 3, because on the other side it's supposed to be 3. So that means that 1, 1 doesn't solve equation 1. Well, if this doesn't solve equation 1, well, it cannot solve both of them, because it already doesn't solve one of them. So that's what I'm writing simply. 1, 1, cute, is not a solution of equation 1, hence it is not a solution of the system. Okay. I don't even need to check for the second equation. Oh, by the way, it's not solving the second equation. 2 times 1 is 2, minus 1 is 1. That's not 4, so it doesn't solve the second equation either. The point being, as soon as our proposed candidate doesn't satisfy one of the equations, well, it cannot be solution of the system. So that's something important to realize. Later on, we will see that 1 and minus 2 was actually the only solution for this system. Okay? For now, you don't know how that works. You could fight a little bit with the equations and find that out. Later on, we will have a systematic method that will help us figure this out very quickly. So that was one example where we had a system that has unique solution in this case. We still don't know how to find it, but we will learn that. Another one, so simple one. So let's say I have something like this. Only one equation and two unknowns. So x1 and x2 are unknowns. Find the solution. Well, you see if I put 1 and 0, that's one of the solutions. If I put 0, 1, it works still. If I put 2 minus 1, it works. If I put minus 1, 2, it works. If I put 7 minus 6, well, it works. So you see you have a lot of solutions here. So how do I find the solution? Well, if I do what you would do normally, you'll send this guy on the other side. So what I'm going to do is something like this. Okay? So x1 is equal to 1 minus x2. So you give me a value for x2, let's say 6. I'll find you the value for x1. So if I have 1 minus 6, that's going to be minus 5. So minus 5 and 6 gives 1. Yay. So this way, okay, it's simple, but the idea behind is I have one variable that depends on another variable. So this one is called main, this one is called free, because I can put any real number here. Okay, that's why it's free. But x1 is linked through this equation, this expression. Obviously, you could do something similar. You could say that x2 is equal to 1 minus x1. Perfectly legitimate, there's no problem at all. You'll get the same solution. Wow, but that's very interesting. If I get the same solution, that's about, there's something special about it, because that means I have same solution set, no matter how I rewrite it. So solution set is something interesting. So here, now this is interesting part. So a solution of the equation, because okay, it's just one equation, it's not really a system, is, so what is the solution? Well, since I have two unknowns, x1 and x2, solution needs to contain x1 and x2, right? Equal, so x1 is this expression, 1 minus x2, and x2 is x2. And then we will say x2 is a free variable. Why? Well, because it's free. It can take any real value. So that's why, so free variable means the variable can take any real value. But x1 needs to be calculated using this expression. So if I have x2 that is free, it can take any real value. There's infinitely many of them, which means I have infinitely many options here, and this option is 1 minus what I chose at the bottom. So that means that I have infinitely many of these couples. And that's where it comes from, the infinitely many. So the equation, this one has infinitely, infinitely many solutions. Ta-da! Okay, this one was easy. We will see other examples where I have more than just one equation, obviously. But the idea being here to realize that you have one variable that depends on the other, and the other one is free, and it takes any real value. So that's where the infinitely many comes from. And the dependent variable is given by an expression. So this will be characteristic for everything we are going to see. So that's cute. And last one, just to see one example where a system doesn't have a solution. So that's one of the three possibilities. So let's say I have x1 plus x2 equal to 2, and then I have 2x1 plus 2x2 equal to 3 for fun. So I need to solve this. For now we don't know how to solve, but let's say you would be fighting a little bit. So you say, okay, let me find x1 from the first, then plug it into the second, then I will work it out. Okay, let's try that. So this is baby style. You don't know anything, so it's fine. Very soon we will learn how to do stuff properly, so you will not need to do things from high school. So from equation 1, x1 is equal to 2 minus x2. So plug x1 into equation 2. How that looks like? Well, it's 2 times x1. Well, x1 is this, plus 2x2 equal 3. Okay, fine. So distribute this, 4 minus 2x2 plus 2x2 equal 3. So these two guys, bye-bye. Oh, 4 equal to 3. Oopalai. Well, this is definitely not correct. So this is a contradiction. Well, what does this mean? Because this is not true. We know that 4 and 3 are not the same. Well, that means that these two equations are not compatible. Or in other words, you can say that they are in contradiction. What does that mean? Well, that means that this system doesn't have a solution. So there's a contradiction in the system. That means that these two equations are contradicting each other. the system does not have a solution. Ta-da! So this system doesn't have a solution. So that's what it means when you end up with a contradiction. Also, how you can read this is that my variables x1 and x2, at the beginning they are free, they can take any value, but then we put first equation. So suddenly they cannot be just anything they want. Like x1 and x2 cannot be 1, 1. Oh yeah, they can. They cannot be 2, 1. Oh, because here it would not satisfy the equation. So suddenly you see the values that x1 and x2 can take at the same time. Well, those values are limited. So we are putting constraints on possible values of x1 and x2. Each time we add a new equation, we put another constraint. And what this means is these two limitations or constraints that we are putting on x1 and x2, well, they are in contradiction. That's why we don't have a solution. An analogy would be, I tell you, okay, give me a real number that is greater than 1. You say, okay, no problem, I have infinitely many of those. I say, okay, but now give me a real number that is greater than 1, but also at the same time smaller than 0.5. And you go, well, how do you want me to give you a number that is greater than 1 and at the same time smaller than 0.5? You have a problem in your head? There's no way I can solve that problem. So that problem doesn't have a solution, doesn't make any sense. Well, that's what's happening with the system here, something similar. These equations put constraints on variables, and the constraints are just incompatible with each other. They are in contradiction. They are such that nobody in the universe can satisfy them. So that's why the system doesn't have a solution. So that's the illustration of the three options we have when we deal with linear systems. Either linear system has no solution at all, it has one unique solution, or it has infinitely many. When you have infinitely many, you have a free variable. So this is all the vocabulary, and we will revisit this several times with other examples and other systems.